Hello, guys. Welcome back. So today we have a special guest with us, Anik Chakraborty, and I will tell you the reason why I arranged this, and we will be arranging this in the future. So our students and students all over India have something called bachelor's project. So this project actually tests your creativity based on the knowledge you have gained in your bachelor's. And many students face issue in finding project ideas. Okay, how to do that? So what we have decided is that to show what our what our what your past seniors have done in the whole paradigm. So let's get started, and we have Onik with us. We will be watching him, and we will be asking questions to him about the projects he has done in his bachelor's in statistics. He has done his bachelor's in St. Xavier's College, Kolkata, and he's pursuing his master's in statistics from IIT Bombay. Hello, Anik. Welcome back, and it's really great to have you on the show. Thank you for coming.
Thank you, Srijita, for calling me.
Yeah. So let's get started, Anik. So what project did you do on, like, what was the idea, and let's explore together.
We knew it from our second year that we have to do a project in our last year of bachelor's. So we are allotted a few guides under which we are doing our project.
Mm-hmm.
So my guide told me some project ideas which I can choose. So one of them was took a data and analyze the data thoroughly, and other was some research based theoretical project. So I chose
Okay.
the second one, and my topic was importance of Cauchy distribution in the field of statistics, and
Okay,
with that
that's
I
great.
went on.
Okay, so can you show? So Onik will be presenting his work and his final report, and we'll be asking a lot of questions to him, and maybe bother him, but and then we will learn all together. So can you proceed through the slides you have made, Onik,
Yes.
like the work you have done? Yes, perfect. So importance of Cauchy distribution in the field of statistics. Great. So number one question is that where did you make this whole thing, like this report? Is it in overleaf, like LaTeX file, or
Yeah,
it's doc?
it was made on LaTeX using
Okay. So do you
extruder.
suggest your juniors to do the same too, and others, like
Yeah,
other people?
yeah,
Okay,
because
that's great.
some of us used Word also, but LaTeX file is looking good actually. The presentation is good.
Yes, yes, it's really beautiful, and it shows your professionalism and great, superb. So
Yeah.
importance of Cauchy distribution in the field of statistics. So why did you use Cauchy distribution?
Because there are several distributions in statistics, and most popular distribution is normal. But
Mm-hmm.
in many real life cases, the normal distribution is not well matched with the data in hand. So
Mm-hmm.
I think it is good to choose a distribution that is quite deviating from the normal distribution and behave strangely from the normality properties.
Okay, okay. So did you read some books or papers that motivated you, or it just like Kochi distribution came into your mind and you started doing it? Like, how did you start the journey? Like, be so sure that I will take the Kochi distribution. What's your pre-work to do this? Like,
Yeah, because in my bachelor's and +2 level also I study statistics, and Cauchy distribution is one of the untouched distribution that I can say.
okay,
Uh, Very few works have done on Cauchy distribution, and I think I can throw some light on it as well.
oh,
So
that's
I
great.
choose the
That's
Cauchy
great.
distribution.
So let's see what you have done. What's your idea on this? I'm really excited to scroll through your
Yeah.
work. Please go ahead, Anik.
So this is the contents page.
Okay. That's really good organization. Okay, so
It is the introduction.
yeah, so I read this line that it has been developed. It comes from the distribution of physics. So do
Yeah.
you remember like from where it came in physics? Like
Uh, as the normal distribution came from measuring the distance between some stars and some astronomical
Mhm.
errors
Yeah,
in the
gosh,
in
this that, yeah, right.
Gaussian, yes, Gaussian distribution came from that way, and in Cauchy distribution came in other way. Like there are several branches of mechanical and electrical theory and
Okay,
measurement problems,
okay,
and also in financial field some risk distribution are following some extreme distribution which can be modeled by Cauchy.
okay, that's
So from
interesting.
that,
Okay, okay, I didn't know that. That's really great. Okay, so that's great. So it's like Cauchy distribution has a applied origin in physics, and then all this is I have told mechanical, electrical, and physical anthropology. Okay, so I think students can search it up like how Cauchy distribution came from physics and this field. Okay, did you discuss in your work this or how where it's used? It's like a theoretical.
not fully. Actually, I focused on the properties and the uses of Cauchy distribution
Okay,
actually.
okay, okay, that's
So
great. Okay, let's understand the theory. So students, so the takeaways that are future work that you can do, students, is that from where like the applied region from where Cauchy distribution has arisen. Like he has mentioned physics and other is electrical, mechanical, electrical, physical anthropology. So did you give references to this or yeah, or did you give references to this in this work, like the applied part, or then students can find it is otherwise easier, otherwise they can search it online, of course. So yeah, so this can be a future work idea that students can do. So yeah, let's go ahead with Onyx work that he has done. Yes.
yeah. So this is
Okay, okay, so you have described what the basic PMF, PDF, and CDF are here. So
yeah,
what is a basic
theoretical
distribution?
distribution.
Okay,
Yeah.
okay, okay, so yeah, please go ahead. Kochi, okay, I find
So here is my
interesting word here. Kochi is a heavyweight distribution in statistics. So, what do you mean by heavyweight? Can you
yeah,
explain mathematically a bit?
heavyweight. I mean, because one, I can say that Cauchy is really important distribution in statistics, and other way I wrote it because it is the extra very out of very few extreme value distributions. Cauchy distribution is more popular as a outlier distribution, and it has some interesting properties as well. Those researchers can work in future days. So in that case, Cauchy is a weight
No,
distribution
I
actually.
think heavyweight means what mathematically means that the tail probabilities is heavy, like, or is it like that, or um, heavy tails
Yeah,
is like maybe, yeah, maybe I don't know.
uh, yeah. Actually, I didn't mean it in this.
Okay, okay, no worries. Let's go. Let's get started with this whole thing. So yeah, maybe so heavyweight means it has what he mean. Maybe it's an extreme value distribution. So Ronnie.
I mainly focused on the importance. The
Okay,
Cauchy is
okay,
very important actually. Heavyweight means important.
okay, 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 okay. I understand. Okay, okay, okay. Let's go. Let's go to what in the let's go to the literature review section.
Yeah.
So history of statistics, Cauchy distribution. Okay, this is an interesting reference. So note this that Daniel Block in his article, a note on estimation of the local parameter of the Cauchy distribution, describe different procedures for estimating local parameter of Cauchy distribution. Okay, okay. Order statistics. Okay,
Yeah.
so Daniel Block and V.D. Bonnet, these two people have worked on this Cauchy distribution a lot and their properties and estimation, statistical properties. Okay, let's get started and then see what's there, what's unfolding in front of this.
This is the project started.
Okay, yes. So I that's what I told. It's meant for thicker tails. That means heavy weight on the, on the, it's heavy
Yeah,
tail weight.
yeah,
Like, yeah, it has
yeah.
probability x greater than equal to x. Like the one minus the CDF, I guess. This is larger than, like,
Yes, yes, yes.
great. So yeah, you have described the density. Okay, okay,
Density and the genesis of Cauchy.
okay. This is interesting. It's called the Virchow. Can you go above? It's called the Virchow.
Yeah,
Virchow Agnesi. Derived from the
yeah,
Italian mathematician Mario Agnesi, he has described properties of Cauchy curve. Okay, okay. So this is very interesting. You see, the Cauchy is becoming very high peaked. Okay,
yeah,
so as the k value is increasing, it's becoming,
yeah.
yeah, k value and a
More
value
big.
both. Yeah, sorry, k value is decreasing. It's becoming heavyweight. Sorry, it's becoming high. Okay, okay, okay. That's interesting. Okay, okay. So please go ahead.
Yeah. This is some background of for developing Cauchy distribution.
So
So how the
Simeon,
Cauchy
yeah, please
came.
go ahead. What's an interesting point here?
Yeah, the we all know the method of least square or the principle of least square.
Yes.
So there is an assumption we took that the errors are distributed normally
Uh-huh.
when the testing procedure arises. So in that case, Poisson showed that this normality assumption is not correct actually. It may be other distribution the error can take also. So by Cauchy distribution, he proved that by
Okay,
using
so
Cauchy distribution.
Poisson showed that the large sample justification of least square theory.
Yeah,
So okay, the large sample justification of least square theory uh, is not valid representing the characteristic function of the Cauchy distribution. Okay, that's interesting. So I'm just thinking, like, what is meant by the large sample justification of. So Poisson observed that the Cauchy distribution has certain peculiar properties, and Legendre's large principle of least square with the assumption of normal error. Principle of least square means the errors follow the normal distributed errors, and then the best estimator is like summation, modifying the summation of yi
yeah,
minus
yeah,
that line, like estimate the parameters,
yeah,
and we will, yeah. So who have learned regression, they will understand this. So maybe a Laplace large. So he maybe Laplace showed that the errors. Okay, I understood. So I think what he showed that this least square is same as the MLE, right? Under the normal error
yeah,
justification.
yeah, yeah,
So
yeah. Actually,
an MLE has a very good large sample, like it converges asymptotically normally. Okay. So I
yeah,
think what Poisson meant that for the normal asymptotic convergence of the least square estimates, it's not valid. Maybe the variances and all those good estimated terms and the large sample behavior of the least square was not valid if we took the error of normal distributed. Okay, if we took the error of Cauchy distributed,
caution.
that's what. Okay,
Yeah,
that's interesting. That's interesting. So he, okay, the distribution became asserted that Cauchy has responded to the criticism of Benyamin, an article showing Legendre's least square fails to provide the most probable results. Okay. Okay, so essentially, I think Cauchy distribution gain its fame from this understanding that this change of this whole changing the normal error by the Cauchy errors and showing that the properties. Okay, that's interesting. That's interesting. Please go ahead.
yeah. So here are the probability laws, that is the density and distribution functions.
Yeah, this is very. This is something people know who are acquainted with
Mm.
probability distributions. So this is the PDF and the
Mhm.
CDF. Yeah, please go ahead.
And this is the graphical representation of PDF and CDF
Okay. The mu
for
is the
different
location and
devices.
sigma is the corresponding. um,
Scale parameter.
and as you can see, as sigma is increasing, it's becoming much more dispersed. So Cauchy is a symmetric distribution around its mean, right?
Yeah.
Yeah, because it's even it's an even x minus mu whole square, so it's even around x is equal to mu.
Yeah.
Okay, that's interesting. Okay, please go ahead. Yeah,
Here are
I
the
think this is the
interesting
reason why.
properties.
Okay, I now understand why people have modeled using Cauchy, because this is the reason why, the error can also be modeled by Cauchy. The heavy tailed errors in normal, the tails are not heavy. Okay, so you can show the tails goes down exponentially. But in case of Cauchy, can you just go back to the CDF form once?
Yeah.
Yeah, so you can observe the CDF. So probability x greater than equal to x, it's 1 minus. If you take this, it's, you can understand this, it's tan inverse. So it's not going down exponentially to 0, right? But in case of normal, you can show that it's going almost down to exponentially in some sense. So this is interesting. Or I'm not sure about this result, but it seems like it will go down to exponential by the PDF format. I'm not, again, like mathematically, I may be wrong. This statement can be wrong, but yeah. So essentially, what I understood and what Onik meant in his work is that in case of, Cauchy can also be used to model errors, because like the mu is equal to 0 Cauchy, because in that case, if you have heavy tailed errors, like where the errors have more heavy distribution on the other, it's unlike exponentials, it's like more also plausibility on the other hand side, on the larger values. Okay, that's great. So yeah, you understood the reason why Cauchy zero, mean with mean zero, can also act as a error distribution in apart from normal. Okay, please go ahead, Onik. That's interesting.
So here are the interesting properties. And
Okay.
first come the nature of the curve. It is
Okay.
bell-shaped, symmetric about
Mm-hmm.
mu, and as we all know now, the tails are much thicker.
Yes. Yes. So good. That's great. So okay, then you prove the symmetric thing. Okay, so you did the
Yeah.
proof part of this, and proof of symmetry. Great. Can you go below down? So you, okay. So the next part is that it does not. The moments doesn't they don't exist. Okay, the moments don't exist, and this is an interesting property. The moments and the MGF don't exist of the Cauchy
Yeah.
distribution. Yes. So an intuitive reason why the moments may not exist is this, guys. So do you have an intuitive reason why, Onik? So then I can
Yeah.
share.
Yeah. Actually.
Yeah. What's the
So
intuitive
if
reason? What you have in your mind?
so, we
Yes.
divided the expectation of modulus x to the power r in two parts. That is
Mm-hmm.
the bounded part and the unbounded part. So the bounded part, the integral will converge anyway.
Yes.
But for the unbounded part, the integral will not converge in, as there the probability of modulus x greater than equal to k is not going to zero.
This is for R. This is for any R.
And, no, this is for r
Greater than equal
mod
to
r
one.
less than one.
Model less than one or greater than one.
Less than one. Greater than one.
Yeah, I
Sorry.
think greater than one. Yeah.
Yeah.
Yeah. So yes, so that's interesting. So mod r greater than equal to one, the moments will not exist, and you can understand this is, so if you imagine normal instead of the PDF of Cauchy, it's exponential. So the integration, like you can imagine, like the integration of exponential exists. Okay, it's just like summation of exponential exists. It's GP. It's behaving like GP, right? Geometric progression, or the equivalent continuous exponential geometric progression. But here it's not GP. It's like, you can understand it's one, like it's something very positive, like x to the power something. So x to the power x to the power r minus 2. So if r is greater than equal to 1, it's r minus 2 is greater than equal to minus 1. So you know that for x or
Yeah.
r minus greater than equal to minus 1, it converges, like it diverges as x is becoming more and more. So we know this. So therefore, what is meant, what Anik meant is here mathematically, is that understand that since it's heavyweight. Okay, so it's a heavyweight means the probability of the PDF is more on the, on the larger values. So therefore the average, if you take the average, it will blow up because the probability on the larger values is more, right? The higher values have
Yeah.
more probability. So if you add them up, the even weighted it will blow up. So that's the best part. So Cauchy distribution in the moments exists, does not exist because it's a heavy weight. You understand in this way, because it's the
Yeah.
weight is heavy. It's like it's taking larger values with more probabilities. I think that's what he meant in this, and he has explained beautifully by this method. That's great. Yeah, please go ahead to the next one, Onik.
Yeah.
Okay, yeah, please
So
explain.
to overcome the previous problem,
Yes.
another distribution comes into picture, that is truncated Cauchy, which can be obtained by shorting the support of the distribution into some finite interval, like
Okay.
I have chose here minus k to k for some k positive
Mm-hmm.
and finite.
So how do you do
So here
this?
we can, uh,
Yeah, okay, okay, great. Okay. So did you find out any properties of this? I understand. For real life experiments, he's telling that he's telling you that if you're trying to model anything with Cauchy distribution, but it's truncated, you can use this. But here in this case, the moments exist. That's great. Why the moments exist? Because you understand that x
the
greater than or equal to,
I1,
yeah,
yeah, the for the previous, the I1 converges, and here I2 vanishes actually,
exactly. Very
because
good, very good. Yeah,
the
it's
PDF is
beautiful.
0.
Yeah, yeah.
So all the moments exist for truncated
Mhm.
Cauchy.
Okay. Yes. So you have done about quantile something.
Yeah, I have calculated the pth quantile of Cauchy mu sigma.
Mm-hmm. Pth quantile. So what is the definition of quantile? Can you just so it's a probability. Yeah. Please go ahead.
Yeah, the probability of the random variable taking the value less than xi p, here the pth quantile is xi p, less than xi p is p, and greater than xi p is 1 minus p for continuous distribution.
Okay. Yeah. Great. It's pi into p minus one. So okay, okay, good, great. So when it's equal to one, it's infinity. P is equal to one, it's infinity. Yes. So
Yeah,
that makes sense. So do you remember the quantile of normal? Let me search the quantile of normal. So why I'm taking normal is that, so the point Poinshu has made, if you remember, the whole thing, the Cauchy distribution was built, so I'm built on the distribution of as a better error distribution, right? Onik has what has mentioned,
yeah,
and
yeah.
and extending the normal for heavyweight thing. So for normal distribution, the quantile of normal distribution, let's see. So of course we cannot remember this. We need to normal distribution quantile. Quantile. I'm not getting the quantile thing. Yeah, quantile. I got it. So it's similar like mu plus sigma root 2 ERF. So what is ERF? ERF is a special function. ERF
Actually,
is,
this,
yes. See, ERF is it's some integration 0 to x e to the power minus t square. So here it's tan. In that case, it's some e to the power minus t square integration. So you can understand that in case of normal, so the one exercise for you guys can be understand this tan x is better or ERF x is better. Like better means which is larger. So since Koch is a heavy tail distribution, okay, so the probability of 75% will be achieved a bit later than normal,
yeah,
on the bit on that other hand side on than normal. So that's my guess, because till 0.0 till 0, the mean it's 50-50 for both, for normal and because it's a symmetric distribution. Till mu it's 50-50. The median is same. So therefore, for achieving the 75%, the normal, since it's a less weight distribution and more is towards a mean, like less heavy weight, it will be the where it's achieved, it will be much closer than where the Kochi is achieving the 70% P, like, or any P. You can mathematically show that. So just came to my mind that, so these are certain research problems that you should think yourself and you can try it out. So this whole thing is dedicated towards the two students, right? So we are trying to understand that what Anik has done, of course, what's interesting points, but the whole point is helping students understand that how to think and how to make a good BSc project. Yes, Anik, please go ahead.
Yeah. Here we
Okay.
calculate the median and the quartile deviation.
Uh-huh.
Interesting, the quartile deviation counts out to be sigma, which is the
Oh,
scale parameter of Cauchy.
that's interesting. Is it the same for normal? I don't think so.
And no, no, no,
Okay.
not in case of
Maybe it's
it
okay.
is
So you can
0.67 sigma.
okay, okay, okay. It's something else. But it's interesting. So Q3 minus Q1 turns out to be sigma. So if you remember, guys, if as far as I remember, I forgot in descriptive statistics. If you remember, Q3 minus Q1 was a dispersion metric. Apart from range, Q3 minus Q1 for
Interquartile
sample,
range.
yeah, it's a description metric. So you can understand also Q3 minus Q1 by 2. That also it gives an idea about dispersion of the whole distribution. So that's an interesting point to note. Yeah. So in this case, Scotchy, it's interesting. Okay. Okay, mode. Let's say unimodal. Okay. Yeah.
As from the shape, we can see the Cauchy is
Hmm.
unimodal as it is well shaped, and the mode is the point of symmetry or the line of symmetry that x equal to mu.
Absolutely. Absolutely.
And here we can find the mode by calculating the derivative and comparing with 0, and the mode is come out to be x equal to mu, and the modal value is 1 by pi sigma.
Okay. So that's interesting. So what Onik has done is in his entire work, he has taken the most interesting result, the important results, and proved it. Mathematically. That's one very good way to the theoretical project you have told. That's really one great way to proceed in the BSc project. Yeah. Okay. Next one, please, Onik.
Here comes the points of inflection.
Mm-hmm.
By points of inflection, I mean where the curve changes from concavity to convexity or otherwise, or vice
Mm-hmm.
versa. So this points is calculated by calculating the double derivative and comparing with
Mm-hmm.
0.
Mm-hmm.
So
Can
this
you show that?
counts out
Yeah.
to these
Okay.
2 points. These 2 points are actually symmetrically placed over the real line.
Okay. Can you just show the picture?
Yeah.
Yeah. So you see the real analysis connection with probability, and you can see that slowly the curve changes from convex to concave that he has told. That's a very good definition of point of inflection. Yes. So you see that it's becoming concave and then becoming convex in doing that portion,
Yeah.
and again becoming concave. That's so great. Yeah. Okay. So now coming to the interesting portions, the properties of Cauchy.
Yeah. The sampling properties. One is if x is following the Cauchy 0, 1 distribution, its inverse is also following the same distribution.
Mm-hmm.
So, and here is the proof by the transformation technique, the Jacobian technique.
That's great. So I think this has really helped you in brushing up all the probability knowledge and statistics knowledge that you had to do the proofs yourself, and I think it has really helped you, right, Onik?
Yeah, actually.
Did you do this after your IIT jam or before your IIT jam?
No, after my jam exam.
Before your ISI. Okay. So how much time did it take on average to do this, the whole thing?
Uh, about it took about 2 months.
2 months. That's great. Super. Okay, please go ahead.
So here the visual representation of the
Mm-hmm.
above mentioned property.
So how did you draw these pictures? Like which computing software you used?
I used R software, and by taking some random sample from X and then calculating 1 by X, I have drawn 2 histograms and fitted the
So
Cauchy
did you
0,
use
1 curve over.
ggplot?
Yeah, ggplot.
Great. So did in like in your college did they teach you R or you learned it yourself?
Basic R was taught in our course in fourth semester, and the advanced portion was learned by him myself.
Okay, that's great. So did you learn your R while doing this or did you learn R before this? So why I'm asking this because many students ask me, Onik, that how to start learning R. So I personally think that believe that doing projects is the best way to learn R. So what's your take on that?
Yeah, actually, I first learned R and then started doing the project. But in many cases, I have seen that people started doing the project and then tried to learn a software. That is a good way. But one drawback is that the project needs a bit long time actually, because you have to do the project and simultaneously you have to learn a new software as well. So it
Mhm.
takes a bit long time.
Okay. So what do you suggest to students?
I would suggest if you have basic knowledge of a software, then you can proceed with the project and then explore it while doing the project simultaneously.
Got it. Got it. Just a few words on R. So what books did you follow or what resources did you follow for learning R?
Actually, I didn't follow any book or course
You just search
after
on Google.
my yeah. I just took a random data from different websites, and while doing
Nice.
analysis, I learned out by myself.
Yeah, I think that's the way we are all learned. Yeah, 90% people learn that way. Okay, so the next property x and y are standard Cauchy. Then x plus y follows standard. So the variance gets added up.
Yes, yeah, the same distribution as 2x.
So I forgot. Like, is sigma the variance? So is sigma the standard deviation of Cauchy?
No,
No, right? But still, it follows like behaves like the Cauchy too. Like you
Ye-
understand.
yeah,
And
yeah,
the variance get added up, right? So that's interesting.
yeah.
So you used additive property of Cauchy. Okay, now you use 2x. Okay, so you use 2x. Okay, fine, great, got it. To find the
The proof of additive property is done later in the appendix section.
got it. Okay, great. Can you move on to the next property?
Yeah, next property, right? But from this property, we can lead to a conclusion also. That is the variance does not exist.
Okay, this is interesting. Just can you just stop for here for a few seconds? So this property does not
Yeah,
hold
yeah,
in for any distribution, such as this is a unique and interesting property of Cauchy. Also, we can justify this property that Cauchy distribution has no finite variance. How can you do that? Can you come again?
yeah. So
So
if we
x plus
calculate the
y is equal
variances,
to 2x. Oh, this is interesting. Lovely. Oh, this is beautiful actually. Great. Nice.
yeah.
This is a really great. Thank you for sharing that. I didn't know this. Yeah,
Oh,
superb. Like I didn't know like how, yeah, you can prove it this way. This is fun. That's great. Okay, so that's great. Great. Okay, perfect. Yeah, please go ahead. So then you have done using
yeah.
R, the distribution of
Uh,
that.
the visual representation, yes. So now comes the comparison of Cauchy and normal.
This is what I was interested in because you understand that was the apparent, where we started, the source, that Cauchy and
Yeah,
normal are different totally. Okay, please go ahead. In parametric inference, we use normal and parent distribution and derive test rules and confidence interval. La. Nice. And Cauchy distribution is a distribution which may not be used frequently to deal with the real world problems, but can make us understand that fair assumptions or normal cannot yield satisfactory result always in the domain of parametric inference only. That is why Cauchy distribution is so much important in inferential statistics as apart from. Okay, that's great. So we are now comparing Cauchy and normal. I'm very excited to see what unfolds here too. So X and
yeah.
Y.
So
Okay.
following normal and Cauchy respectively.
Okay, the
So
PDF
if
is
we
this.
compare,
So this is really great. So this is what
yeah,
I wanted to make you understand. See, the yellow one is normal and the blue part is caution. You can see easily that normal is much more concentrated in the in the around the mean, while Cauchy has heavy weight. Okay, so although they are so this is what the basic idea is. For error distributions, for distribution errors, you need a mean zero. Okay, and
Yeah.
now errors can be heavyweight or low weight. It's you can use that. For example, I'm not something is not coming to my mind. So an example of heavyweight, like where it's probable that large values can be taken. Okay, anthropology, I'm not sure, but anthropology can be one of them.
Yeah, one example can be in the field of financial statistics
Mm-hmm.
where the risk comes into picture.
Mm-hmm.
So the probability of mm, the risk distribution can be heavy tail, because there is certain cases where risk can be heavy in a higher portion, or risk can be very much low. So the extreme values comes into risk analysis.
Okay, that's nice. I didn't know that. I'll probably make a content on that. Thank you for the idea.
Okay.
Yeah, that's interesting. Okay, please go ahead. So the basic idea, can you just go on with the picture? I want to make something like, so people who are learning to trying to learn probability understand the area under the curve is one. So you can see that how if you put the sand, like the same amount of sand is there, you can imagine how if you try to put the sand on the tails, it's the height is becoming shorter. If you put it that, like if you want to gather it up around the mean, the tail is becoming small. So this is a
Yeah.
basic idea, that's one you can understand, like integration of the area under the curve is one. Yeah, please go ahead, Anik. Okay, mean median mode you understood. The got a thick
Oh,
tail. Okay, as discussed. Okay, yes, you're right. Okay, perfect. So you're doing a simulation study now.
yeah.
So you're taking a sample size.
And the empirical levels of Cauchy and normal.
Mm-hmm. So taking these samples, what is the empirical level of? I didn't get you.
Empirical levels means we have a given level of significance, which I took here 0.05, and from that I calculated how many times the definition of level is supremum supremum of beta belongs to the parameter space, probability, the parameter, sorry.
So I understood. Maybe I will help you out. You have done this a long time ago. Maybe you've forgotten a bit. So I think it's like it's kind of the sample version of p-value. Do you mean it's not p-value? The
Yeah,
quantile thing, sample
p-value,
quantile.
sample version of the chosen level of significance. So
So
how
do
much
you?
error we are, how much type 1 error we are allowing.
But I'm not understanding the test. So I personally, what I think, what I know, what my guess is that for Kochi zero
Yeah.
1, so what I understand is that if you take a 0.05, so it's
Mm,
telling the Kochi is telling the probability, the point
mm.
after which probability is zero is greater than equal to that point, like the x, the values under the Gaussian normal as the x, such that probability x greater than equal to x is equal to the level, the 0.05. Do you mean by that?
Yeah,
Okay, so it's kind of the p-value kind of thing, and the exactly the sample quantiles maybe, like inverse of the 1
yeah,
minus
yeah.
sample
Sample
quantile.
quantiles. Yeah, sample quantiles.
Yeah, it's kind of the sample quantile. So great, great. It's okay. So I understand you have done this a long time ago, so you may have forgotten. It's totally fine. So it's discussion and discussing with the students. Okay, so you can
No,
understand one thing
actually, that
interesting. Yeah, please go ahead.
yeah, the testing problem here was our test of mean, where in null hypothesis I took mu equal to 0, and alternative hypothesis mu equal to 1.
Yeah.
So the
Okay, did you
testing
write
problem
this
I took,
somewhere? I'm not sure.
No, 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 no.
Okay, I think
didn't
probably
mention.
students, it's suggestion for the students that who will be doing this. So if you write this kind of thing, you should mention this so that it's like gladly his teachers didn't observe this, but it would have been great if you have written this. Yeah, but yeah, but the basic
Okay,
idea,
okay.
yeah, but the basic idea, I think that you can observe that the Cauchy for that same level of significance, like the probability Cauchy has larger value. So it's saying that maybe it's like yeah.
Yeah, ideally, as the sample comes, as the normal assumption is to, I took the normal assumption, so the ideally the empirical level should be close to 0.05, which is my chosen level of significance. But in case of Cauchy, it is going to increase to 1. So
Okay, okay, that's interesting. Okay, okay, okay. I understood your point now. So it's kind of showing also the heavy tail aspect of Cauchy.
yeah,
Yeah, so same point from after we it's 0.05 for normal, it's going to a larger point, it's going to 1, like instead of
yeah.
0.05 to attain the same level. Okay, that's great. Yeah, please go ahead.
So here comes the estimation part. First comes the unbiasedness. So we know that the
Okay, estimation
bias
of
estimator of the population.
yeah. So we know unbiased sample means unbiased, but in case of population, some population mean does not exist, so we cannot use the fact here. So instead of for this Cauchy sample median is used to suitable estimate the location parameter. That's great. Yeah, that's fun. So how do you estimate this sample mean? By order statistic.
Yeah,
Sample median,
sample median for, I have shown it for
odd.
odd sample size.
Yeah. So you have found the
So
order statistics distribution.
yeah, so
Okay.
median becomes x order x plus 1, k plus 1.
Okay.
So the distribution of median is symmetric about
Hmm.
x equal to mu. So I have used one property here that if for any symmetric distribution, if mean exists, that is the point of symmetry.
Hmm.
So
So you have shown that's so beautiful. So the sample median. So I think he has shown it before that the mean and the median and the mode are all equal in case of Cauchy and normal both,
yeah,
right?
yeah,
So he has
yeah,
used this property to show that the sample median is unbiased. That's really great. Super. To get the location parameter
yeah,
because the moment does not exist here. So you cannot use method of moments estimated too.
yeah.
Okay,
Sorry.
it's okay. So that's so beautiful. So you can see the various ideas have gone through this. The sample mid range. Okay, what is this?
This is the minimum, the average of minimum and maximum.
Okay, it's also coming unbiased
Yeah,
for the location parameter mu. Okay,
yeah.
that's great. And
And I have mentioned some other estimators which the audience can research. There are quick estimators which are the, this is actually the sample mid range is actually a quick estimator.
what do you mean by quick estimator?
It is the weighted average of the
Okay,
some
okay, okay,
order statistics.
okay,
So
okay. Quick estimator. Yeah, because it's easy to find. Find the maximum, find the minimum, and just add it and divide by 2. Okay.
yeah, yeah,
Yeah, okay. It's summation of wi xi maybe, or maybe it's xi, xi.
yeah,
Or another good estimator
yeah,
of the location parameter is the trimmed mean, which is used as central 24% of sample order statistic and also as a better estimator than the sample median. Okay, okay. I didn't understand this very well, but just give me a minute.
so here we, okay.
Yeah, so it's morning time here. Mom is calling back from India. So yeah. Um, okay, so in our case, it's target to minimize the asymptotic relative efficiency of the constant estimator. Okay, so you have a lot of estimators now. You are trying to find the asymptotic distribution and finding the variance of that because all are unbiased, and finding which one of them has minimum efficiency.
Yeah.
Okay, yeah, please go ahead.
So here is the consistency part.
Okay, using the law
Same.
of large numbers. Okay, you show that sample means the consistent estimate of the population mean. Okay. But in this case, population mean does not exist. So robust estimator becomes consistent for the location parameter. Sample median becomes the robust estimator becomes a location parameter. Okay.
So here is the visualization.
I mean, I will tell you one interesting example. So since understand this, guys. So when you have a data set, the data set can have really high values. Okay. And if you generate some values from Cauchy, you will get high values. So this is also one why median is a robust estimator, because let's say you're generating from Cauchy. Cauchy is a heavy tail distribution, so there's a probability that you will get higher values. Okay, so therefore, if you take the mean, it will be higher, of course, right? So,
Yeah.
but also understand in case of outliers, also the outliers may come from a heavy tail distribution. Okay, so the outlier in case of outliers also it becomes, you know, uh, in case of outliers it becomes like heavy tail too, like, and therefore it can change the sample mean just like it's doing here. So therefore in that case, so that the outliers does not do not affect the estimate of location parameter, they are taking a robust estimator which is median, and you can show that median does not affect the outliers because it's taking the middle one. It's not seeing the values, it's taking the middle one. So outliers are low in numbers, so they're just getting cancelled out. So this is a basic idea what it means by robust estimator. Yeah, and you can showing that robust sample median is a robust estimator consistent with the location parameter. Okay, okay, that's interesting. And you're showing it by visually. Did you prove it mathematically?
No.
Okay, okay. So maybe another work you guys can check out is to prove this mathematically in your own project work.
Yeah, that will be a good work.
Yeah, because I already found out the sample median distribution. So finding probability xk plus 1 minus mu less than epsilon, this will not be a heavy work.
Yeah.
Uh, yeah, and you can show that maybe. Yeah, please go ahead. Yeah, you can see how sample mean is crooked. Sample mean is bad behaving. You can see that. That's a really good presentation.
Yeah.
Thank you for sharing this. Hmm. Okay, so now you're finding CRLB
Yeah,
of.
CRL Koshi.
Okay, so you're
Koshi
first
theta
finding the
one.
information of the whole. What one data point, n data points give the information. So, so finding the information to be pi, what is that, or n, I think information to be, can you go below? So finding the information by all the score functions, all the computations, and he's getting the information to be half. Yes, it was a constant half just for one sample parameter, just for one sample,
Yeah.
the information contained in one sample for theta. What was theta? Can you check once? Can you show, go to once again? So the
Theta
distribution
is
is
the location
location
parameter.
parameters with the, okay, the standard deviation, the whole, it's not standard deviation, the scale parameter is one, location parameter is theta. So what
Yeah.
he's showing, Anik is showing that for Cauchy, the information about theta, the location parameter contained in one sample is half by the idea of Fisher information. Okay.
Yeah.
And then, so you are, therefore you get a criminal lower bound, it's 2 by n. It's
N
okay.
is greater than 2.
So C theta is not an OPEF. So this equality, yeah, I
Does not
think this
hold.
this this is something we have learned, that the equality holds if and only if it belongs to the OPEF, right?
Oh, yeah. Yeah.
Yeah. So therefore, he is telling that since it does not belong to the OPEF, that bound is not attained. So what's, yeah, that's great. So that's a really good point. Thank you. So it's like entire revision of the statistics and everything, statistical estimation. So if you, yeah, great. So, but camera warmer is not attainable bound. Yes, you're right. It cannot be attained because it's not OPEF. So there's one
Yes.
proof. If you remember, the CRLB is attained even only if the distribution is OPEF. You can prove
Hmm.
that using that equality and that covariance structure. It becomes into a linear form, and you can take the log of it. It was a log equal to a linear form. You take the if you take the exponential, it becomes exponential. Then yeah, great. So now you're finding the MLE. So is an MLE coming out to be the median?
No, we cannot find a closed form of the MLE actually.
Okay, okay, okay. We are not finding the closed form of the MLE. So go down, go down.
So we're calculating the likelihood function and by taking the derivative, and so we started initially with the median value.
Okay, so are you using
And
that Newton's method to find us?
yeah,
Okay. So another way of finding MLE you will learn in your future is EM algorithm. So maybe you can use this and transfer into a mixture problem and do EM algorithm to find out, like that can be one way. But I think Newton's way is a better way here because it's all derivative and good things exist. So yeah. So one other idea what came to my mind on it is that maybe you can show that or one can show students can show that what the MLE is it MLE turning out to be the median? What is the MLE turning? I don't think MLE will turn out to be median, but what is the MLE turning out to be? Like how is the MLE like what value like is the MLE turning out to be? How is it like is it turning out to be close to sample mean? It should not. What it is turning out to be? What is an MLE? So what is it's close to? So maybe you can one can be understanding this like you cannot like by a simulation study. So is the
yeah.
MLE turning out to be close to the median, or it's less than the median, or how it's behaving? So because we know that median is a very good estimator here, right? So is the MLE working bad in terms of the median, or it's like so you can find out the relative efficiency of the in a long term for large data samples. Is MLE working better than a median, or what is the basic idea? So in the statistical estimation part, you have quite a few estimators, and you find the relative efficiency. So you can find the relative efficiency of median in terms of the large sample part idea. So that can be a good idea to test. So we discuss a few future progress research ideas that you can put into this work and add in this work, and that can really that can open your mind. Yeah, so one way to do that is like this simulation study. Okay, what's the conclusion? So yeah, you have discussed
So
about what you have done here.
yeah.
Yeah, trying to estimate the scale parameters, multivariate Cauchy parameters, testing procedures, and confidence interval. That's great. Yeah, but this is really good work on it. So now there's appendix, I guess.
Yeah. So the proof of identity property.
Yeah, we can leave this part here. So you can
Okay.
see he has used Jacobian here. So thank you, Anik, for this beautiful discussion. So do you want to add something to what you could have done better, or what you wanted to add but you couldn't do due to time?
Yeah, actually, I tried that simulation problem, which I
Mhm.
did it. This simulation problem, I tried to do a good one, but due to lack of time, I just created the empirical levels. I also tried to compute the mean square error of the parameters,
Mhm.
but due to shortage of time, I cannot do it.
It's
So
okay.
it can be a good work if we could find the MSCs of the estimators, yeah, like the unbiasedness.
Yeah, that's really interesting. That should be interesting. So yeah, I think this can be really interesting work for students out here interested in this theoretical work. So what I will do is I will link Onik's LinkedIn ID in our YouTube video, and you can get in touch with him, discuss with him if you want to take his work and build upon this work for your research projects. Then totally fine. You have to refer his work. Remembering reference is a really important thing in doing projects and research. So you can refer his work in your own work, and you can build upon the extra parts. So that's also fun, and I'm really glad to see people have done really so beautiful work. In my bachelor's project, I have done uh, on cricket and statistics. It was an applied one, but it was really fun too. So you have done the references that to Burnett and Block's work, and Johnson's and Donald Barr's work. That's great.
The book by
Okay,
Johnson
continuous
Fox.
in okay, okay, okay. Balakrishnan,
Yes.
Samuel,
And
and
our all favorite Wikipedia.
yeah, yeah, you're right. It's super good place. Yeah, so good, so good. So thank you for this thing. And okay, so I will ask Onik like about um what is like so did you how much credit did you get for this whole project, so student can get an idea that this is a good estimator of of how much work we need to do.
Created actually
You
didn't
forgot. Okay,
remember.
no worries, no worries. So yeah, so student the teachers appreciated this.
Yeah.
Okay, so
Also, I had to make a presentation on this, and I have to present that file in front of the professors.
that's nice, that's nice. So you have also make a presentation. That's a lot of
Yeah.
work. That's a lot of work. But yeah, so if you want to make a presentation, I think if you do it in overleaf, you can just copy and paste the LaTeX code. So also you will learn a new software, which is will be really important for your all these mathematical things and presentations in the future. So it's like a lot of learning experience for you, and it will be fun. And
Yeah, I will share the GitHub link where I have stored all these dissertation related files. So I'll share that link.
sure, sure, perfect, perfect. So thank you, Onik, for this beautiful discussion. I hope you enjoyed sharing your work too.
Yeah, yeah,
And we had a great discussion about what work you have done, what are the basic intuitions, and what students can improve upon and do, and focus on future research. I think that's where we contribute to the students as a whole, community, about what work they can do. I hope this helps our students in doing projects, having ideas about the projects. And for any idea, anything, you can always reach out to us. You can reach out to Onik, you can reach out to me, and we can of course discuss things that can help you in your career. So thank you guys, thank you Onik for coming over and taking his time out to share his knowledge and his work to the students, and so that it can help them. And yeah, so thank you for joining, and we will see you in the next video, and we will see you in the next live or something. And yeah, thank you, have a great night or a great day, and stay tuned and stay blessed. I will end the meeting here, and thank you again, Onik. Thank you for coming. Thank you guys for
thank you
watching
so
this
much.
till the end. If you like this, please do subscribe, share with your friends whom it can help in their projects and work and get an ideas. Yep. So have a great day ahead. See you in the next video. Stay tuned and stay blessed.